And the floor is yours, Ollie.
Okay, great. Well, thanks, Ed and Christina, and thanks very much for having me here. I hope everybody's had a look at the PDF we're going to be using. I'm going to share screen in a moment and we can take a look at it together. Let me see. Feel free, I'm happy for this. We can structure this how there's a limited group here. We can structure this in whatever way is the most useful to you guys. So please feel free to chime in and to ask questions. Like that's what this is for, right? So, please don't hesitate to speak up. So the fundamentals of this tutorial. So basically what I've tried to do is I've made a low resolution reconstruction of hemoglobin, which I made in CryoSpark from some lovely data from Empire. And this is deliberately rather a poor map and a realistically poor map so that it might, match what you might encounter in the sort of starting phases of a structure determination project. But having said that, it's something that you should be able to build. Like you should be able to take this map and with the prior knowledge that's available in the tutorial directory, you should be able to build this map. And so what I've done is I've made an initial model that's basically been mutilated in certain ways. So I've deliberately misoriented the model in the map. I've removed one helix, the C-terminal helix from chains A and C, and I've replaced the beta chains by alpha chains. And for reference, the reason why I did that is to give you something that is more representative to what you might do when you're solving a structure of a related protein, right? The beta and the alpha chains are similar, but they're not the same. And you can see right here, the alignment between the human beta chain and the human alpha chain of hemoglobin. And I also removed the heme molecules so that we can rebuild those later. And so today I want to go through how we can first fit and then fix this model. So we'll fit it initially in UCSF Chimera, and then we'll fix it up in Coot, or at least start along the way towards that. To start with, hopefully you've all got installed. I think everybody on the call has been here for a little while at this point. So if you had installation problems, hopefully we've covered them. So you should have Coot 0.9 or later installed, Chimera and CCP4, and preferably as well the Coot and Chimera trimmings files. And feel free to follow along as we do this. Hopefully you've already downloaded this file here. So this is the tutorial archive, which has all of the files we'll need. And so if you unpack that wherever you like and open it up, you should get something that looks more or less like this. So you'll have a base Coot tutorial directory, and then you will have in the base directory 2 files. You'll have an initial model and an initial map. And then there are a couple of subfolders with some extra files that you don't need for the tutorial, at least in terms of the extra maps and extra models, but which you may want to consult. Okay, so let's open up the map in Chimera. So let me just navigate to that. So I've got the map here. I'm going to open that up in Chimera. Sorry, my Chimera is a little bit sleepy and takes a little while to load up, but if you give it a couple of seconds, it should awaken. Here we go. Okay, so this is our map. So let me see. You just adjust the threshold a little bit here so that we can see what we're doing. Okay, so the other thing that I didn't, I think, mention in the tutorial. So if I have it set so that it automatically switches to step 1, right? So that is the binning of the map. In your version of Chimera, it might look a little chunky. And if it does, you can just change the step here. So just change it to step 1. Okay. Let me see. Yeah, so if we have a close look at the helices here, particularly, let's say, this one. So, oh, sorry, that command I used, CFR on, that's part of the Coot trimmings. It just allows a more natural sort of reorientation of the map, more precise navigation. And I'm also going to use another one of those commands, SimClip, which just clips symmetrically around the center of rotation. Now, if you have a look at this helix, you should be able to tell off the bat that something's not quite right, because this helix is left-handed, right? And that is something that you will encounter all the time during ab initio structure determination, because there's an equal probability that you're going to converge on the inverse versus the correct hand. So to fix that up, we're going to invert this map, or rather z-flip this map. And so we'll do vop z-flip and then give the ID of the map. So vop sleep z-flip 0. And we now have a map which has nice right-handed helices. Great. So I'm going to open the initial model, which we have here. Let me just show everything. Is this making sense to everybody right now? I can't really gauge whether everybody's following along, but please do jump in if there's something that's not making sense.
So if we have a, say, left-handed DNA helix, we need to use the same command to flip that to right-handed helix too?
Well, yeah, I mean, so this is in the case of protein where you don't have left-handed protein helices. I'm assuming that's also, unless you have some kind of special DNA helix that's supposed to be left-handed, yes, you would want to do this. This is just, it inverts the chirality. So if the chirality is not correct, you can use that command to invert the chirality of the map.
Okay, thank you.
Okay. So you can see here, this is being deliberately misfit, so it's not correct. So we want to move it to the center of the map, and I'll just quickly make this look like it does in the tutorial. So I'm first going to color the model by chain, and then I'm going to display the map as a mesh using this little alias called Coot mode. So now it looks like it does in the tutorial. Okay. Now we want to move this model to the center of the map. So what we're going to do is we are going to deactivate the model, right? So this is the model. We're going to deactivate the map. So this is the map. So I'm going to deactivate that. So you can either do it if you have this set up the way that I do by unchecking this down here, or you can also do the same thing in the model panel in the A tab, right? So we're going to uncheck that one. And now we can move the model with respect to the map. So I'm going to move that over there. I'm going to reactivate it, have a look around, maybe move it around a little bit. The goal here is just to get it in the center, not to make it perfect. Now we're going to do a global fit of this model to the map. So there's a command in Chimera called fit map. You can use that either to fit the model locally around the current position, or you can use it to test a number of different random orientations and displacements of the model in the map, which is what we're going to do now. Okay, so now we're going to do fit map. We're going to give the model ID followed by the map ID. And then we're going to search 100 candidate orientations. in a radius of 5 angstrom. So let's see how that goes. So you can see down here, it's checking out, 100 different fits, and then it's going to come up with a table of all the different fits, which you can see over here. And what we're hoping is that one of them will be a lot better than the others, and indeed that seems to be the case. And you can flick through these in order to see, all the other ones, right? And you can see that these bottom two are almost right, but wrong in the sense that it's fit the alpha to the beta and the beta to the alpha, right? But if we go back to this one, everything looks happy. So now we can clear that list and close. If that did not work for you, which sometimes it won't in a real situation, the first thing that I would try is low pass filtering the map, because that gives you a much larger radius of convergence for this procedure, and so will allow better fitting in the case that the signal was too marginal the first time. So if we wanted to do that, which I can, what we can do is apply a Gaussian filter to the map. So we would do something like VOP Gaussian, give the map ID, so number 1, and give a standard deviation of, let's say, 2 or something like that. And when we do that, we will then get a map that is much smoother and has much lower resolution features. And so for rigid body fitting of a model, if you're in a marginal case, that can be helpful. All right, that's a little digression. So I'm going to delete that now and get back to where we were. Okay. Any questions so far? Everybody's following along, all good? I'm going to assume yes, unless anybody speaks out.
What is the difference? I'm sorry, no question. What is the difference on using that command or using the option in tools in the volume?
Oh, they're the same thing.
The same thing.
Okay. It's just that this is convenient if you're used to, it's sometimes convenient to be working on the command line because you can easily repeat commands, like, by cycling through the history. I just tend to lean towards using commands on the command line because they're just easier to reproduce. But absolutely, you can use a volume filter. That'll do the same thing.
Okay, thank you.
Okay, and if you're following along here, you will want to save this PDB file because we're going to open it up in Coot afterwards. But I have also included a pre-generated Z-flipped map in the extra maps directory and a correctly oriented model in extra models. Okay. Okay, so at this point, what we want to do, and what I would encourage you to do, is to have a look around and just have a look at the overall fit of the model to the map, and just have a look and see, like, if you see any things missing. Is there any unmodeled density? Do some chains fit better than others? Hopefully you can see that is the case. So you can see that this red chain is not fitting perfectly here, right? Like you can see that this helix is not fitting perfectly. You will also notice that on this blue chain, there is a whole helix missing here. So this is the C-terminal helix that I mentioned, which we've deleted. And on this one, you can see a chunk of density corresponding to a heme where the heme is absent. And overall for this red chain, so chain D and chain B, you can see that overall the fit is imperfect because for these, the sequence is wrong. We've deliberately made the sequence wrong. So to give you a little closer view of that, I'm going to change the model to a wireframe, which I like to do for detailed inspection of a model in Chimera. So I'm going to do Coot mode wire, and then I'm going to give the model. And so now I find this to be a more convenient representation for looking at the detailed fit of a model to a map. So it's more sort of Coot-like, and I find this convenient for navigating around. And yeah, hopefully you'll see that the fit in this chain is not perfect. Whereas if we move over to one of these other chains, not this one, we move over to one of these other chains, you'll see that everything fits a lot more nicely. where you can see that this is missing a C-terminal helix, but everything else looks okay. Whereas those other chains I was looking at, there are clearly some densities that are incorrectly fit. Okay, so now we're going to switch to Coot. So we're going to load up Coot, and we're going to load the map and the model that we have just saved. So let me do that. I tend to do this from my terminal because I like having the terminal there for Coot for feedback in terms of any error messages, logs, and so on. But you can do it however you like. Okay, so we have Coot open here. Is everybody at this point? Does everybody have Coot open at this point? Hopefully, yes. If anybody doesn't, or if anybody is having trouble, just shout out. We can deal with that. It's no problem. But right now, I'm just going to open up what we want. So we're going to open up our initial model moved.pdb, or the one that you've just saved. And I'm going to open up the map, so which is in the extra maps directory. And I'm going to open up this one, the original manual Sharp 150 Z-Flip. There are some different maps here which we can compare with, just to show you the effects of different post-processing strategies. So the effects of different sharpening and density modification procedures on the map. In this one, I've just manually sharpened by a B factor of 150. Okay. So I'm just going to change the threshold a bit so that we can see what we're doing. Okay, so just to go through some basics here. So if you've installed Coot trimmings, there are now a bunch of shortcuts and keyboard and key bindings that you may or may not be familiar with, but might be helpful for you. So let's just go through a couple of those. So I've set the square brackets to cycle the representation mode of the model forward and back. So let's just try that. So if I press the forward one, it will cycle through the C alpha representation, or atom representation, rainbow representation, secondary structure plus whatever that is. I don't really know that one, and so on. And you can go forward, you can go back, etc. Okay. I also find it very convenient to be able to quickly toggle the display of the model on and off. So you can do that using the / key. So if I show you that, so that's useful for when you just want to look in context at the map and you just want to quickly turn the model off or quickly do that. You can also use the question mark shortcut if you have multiple models to cycle through displaying each individual model. Likewise, we can do the same thing for maps. So if you use the backtick key, that will rather toggle all maps on and off, which can be useful just for inspecting the model. Okay. And likewise, the tilde key, so it should be shift backtick, will cycle through individual maps in the case that you have multiple maps loaded. We don't here, so I won't show you that one. I've also set up a shortcut to quick save the active PDB. Note that it will overwrite the file that you're working with, but it will make a backup of that file named, whatever PDB, named the file name of the PDB .back or something like that. In fact, if we try that right now, you should be able to see that here. So it's saying we've saved initial model moved. And if this was an accident, you can find a backup of the original file at initial model moved pdb.back. Okay. If, like me, you're using a Mac with a trackpad, you want to make sure that you set emulate 3-button mouse in the Xquartz input preferences. So you can see that here. And that means that when you use Option or Command while clicking, you can emulate what would happen if you had a middle button. So now if I Option click on an atom, it will recenter on that atom, which is what you would do with the middle button of a normal mouse. Okay. So just in terms of some Coot basics, in terms of how to navigate around. If this is too basic for everybody, please yell out, but I'm going to assume nobody knows anything. So you'll want to use control, click and drag to translate the view, and click and drag to rotate the view, right click and drag to zoom in and out, middle click or Option click on an atom to center. And the other thing that's very useful is Control G, which brings up this little unlabeled box, and that allows us to type in an atom, for example, like let's say C88, something like that, chain ID and residue number, and hit enter, and that will take us to that particular location. You can also use Shift click to label an atom or a residue in case you don't know what it is and you want to rectify that. In terms of the view, you can use Control right click drag to translate the slab in and out of the plane, or Control right click, sorry, that was Control right click drag up down to translate the slab in and out, or Control right click drag left and right to change the thickness of the slab. So if I just demonstrate that, you can see now that the slab is getting very thin, right? And then if I do up and down, now that slab is moving through the molecule. Okay. All right. So whenever you load up a model and a map, you're going to want to set some refinement restraints. So if I can do that in the refine regularized control panel. You can automatically estimate the refinement weight. You may also want to manually play around with this a bit in order to optimize the real space fitting into your particular map. You may also want to play around with these restraints, but we won't get into that right now. Okay. So now what we're going to work on is we're going to try to build that missing helix that I mentioned. So we want to navigate to the C terminus of one of the alpha chains. So for example, we can get there by hitting Control G, like I mentioned, and just typing A118. And that will take us to the C terminus of the A chain. Okay. So you should notice that you have a tube of density protruding from this terminus. We can see that right here, right? Clear tube of density looks like a helix, but there's no helix in the model, right? So what we're going to want to do is to go to approximately the center of this helix. So something like that looks pretty good to me. And now we're going to place a helix. You can either do this using the keyboard shortcut H, or you can also do this in the menus. So if you go calculate, other modeling tools, place helix here, that will also do the trick. I typically like to do it using the keyboard shortcut. So we now have a helix here. Great. If that helix happened to extend beyond the density that we think it ought to belong to, let me just make this a bit wider, we will want to trim it a little bit. So in this case, it is extending just one helix long, one residue longer than we want, because we're going to want to merge this seamlessly with this terminus. And you can see that this residue should be followed by that one, right? So I'm going to delete this residue. So we can do that using delete zone. In this case, we're just deleting one residue, so we could just do it doing delete residue, but that's fine. We'll click that once and then click it a second time. And now we have our helix. Let's check the other end as well. This actually looks pretty good. We could maybe extend it a little bit, but let's leave it for now. So for now, what we're going to do is we're going to take this new helix and we're going to refine that into the density. So let me just turn the map off for a second so I can see what I'm doing. That's where that shortcut, the backtick shortcut, comes in really handy. Also, Shift Z will get rid of any annoying labels. And now we're going to refine this using real space refine zone. Right, so we're refining that. I'm going to turn the map back on. So you might notice these spheres. These are a new thing in Coot 0.9, and these represent on-the-fly validation indicators. The spheres represent the Ramachandran favorability. So whether you have favored, allowed, or disallowed Ramachandran values. Okay, everything looks pretty good here in terms of all the traffic lights. We're pretty happy with that. And just in terms of a visual fit, this looks pretty good. You can see that the side chains lining up, or rather the C betas are lining up pretty well with where the side chain density ought to be. So we're going to accept that and go. Okay, so now what we're going to do is we want to merge this into the model. And in order to do that, we need the numbering to match the model. That is, this original model goes 117, 118. So the next residue should be 119. Okay, so I have a little shortcut in the custom menu, which you will have if you installed Coot trimmings, which makes that easy. So after centering on the, you can see here, we're centered on the first residue of the helix we want to renumber. So we're going to go to custom renumber, and we're going to go to, we could do a number of these different things, but let's just say renumber active chain by current residue. So whatever number we type in here is going to become the new number for this residue, and all the other residues in this chain will be altered accordingly. So I just mentioned this should be 119. So we're going to change that to 119. And now all of the other residues in this chain have been altered by the appropriate offset. Okay, great. So now what we can do, let me just move this along. So we've done that. Now what we're going to do is we're going to want to merge this helix into the initial model. Okay. So there are a number of different ways you can do this. I have my favorite way, which is just using this little shortcut. And so in this case, we want to first merge the models, and then we will merge the chains. So here we're going to click merge two molecules, and it says click two, second into first. So that means we want to click, the first one we want to click is the original model that we want to merge into. So we're going to click that one, and then we're going to click the thing that we want to merge into it. Boom. Now that's merged in there. Great. But these two elements are still separate chains. One is chain A, the other is chain E. We want them to be part of the same chain because they're part of the same chain of the protein. Okay. So now we're going to merge the chains, same thing. Custom, merge chains in this case. We'll click the original one, and then we'll click the new one. Now they are part of the same chain. Great. So now we're going to want to assign sequence. So I have a little shortcut for this here. So if you go to custom, mutate active chain to template sequence, this will bring up a little box, and it'll say enter raw amino acid sequence must be complete. So basically this has to match the, this is just the amino acid sequence of this chain, and it has to be numbered such that residue 1 of this sequence matches residue 1 of your chain, if that makes sense, right? So the numbering has to be correct. It's just going to blindly mutate everything according to the position in this sequence. Okay, so we have this sequence here. So if I navigate over to Finder and I go to the MISC directory, we have the sequence right here, sequences.faster. I'm going to open that using not Chimera, just text edit or really anything would be fine, but text edit is fine. Okay, so in this case, we want HBA. So I'm going to copy the sequence for HBA. Don't worry too much about formatting characters. If there are formatting characters there, the script will remove them. But you just want the letters, the alphanumeric characters that correspond to your sequence. So I'm going to paste that in there. This is all good. And now we're going to click mutate active chain to match sequence using PDB numbering. And that's going to go through. And what you will notice now is that although these are still listed as alanines, or rather, they're not listed as alanines. I misspoke. They're still, they still look like alanines. They don't have their side chains filled in. They've all been altered to what should be the correct sequence. So you can see that this guy is annotated as a histidine. This guy's annotated as a leucine. This one also a leucine, and so on. So in a moment, we're going to fill some of those guys in. But for now, what I want you to do is to go to the C terminus of this helix, and let's just see whether we can add any residues to it. So it looks like maybe there's a residue or two here we can add. So we can do that either using the add residue or add terminal residue button over here, or we can do it using the Y shortcut on your keyboard. So if I hit Y, it will try to add a residue. And if I hit Y again, it'll try to add another one. Okay, and I can just try to, you know, refine that back into the map. Okay, looks all right. And what you will notice now is if I repeat that mutation command, so mutate active chain to template sequence, it saves the sequence that you already put in there previously. So I can just load this up, hit enter, and now it will tell me what these ought to be. So it's saying that this ought to be a tyrosine. Well, that seems kind of reasonable. And the previous one ought to be a lysine. Great. Okay, so what are we going to do next? Right, so in a real circumstance, like during a real de novo building project, I find it very helpful to use secondary structure and disorder prediction as a guide while I'm doing it. Personally, I really like the Extel server. I use that a lot. And you can see a screenshot of what that looks like for hemoglobin here. And if you want to have a go, you might want to have a look through and see, you know, how does the secondary structure prediction annotated here compare to the actual position that we know from the structure of the ends of each helix. And I think what you'll find is they're pretty good. And generally speaking, they are pretty good. On a per residue basis, secondary structure prediction is on the order of 70 to 80% accurate. So it's a very good guide while you're building to keep in mind. Likewise for the disorder predictions, they're also pretty good. Not quite as good as secondary structure, I think, but pretty good. Okay, so normally what we would do in this circumstance is we'd go through and fill these in. Shift K will complete a residue. Doesn't seem to be working right now. Oh, sorry, K will, no, my something's must, oh, sorry. I'm getting ahead of myself. Never mind that. Let me just scrap what I said about Shift K. I was having a little brain malfunction. What we want here is we want Shift M. So if you've loaded Coot Trimming, Shift M will load up something where you can just type in the single amino acid code for the residue, and it will mutate to that residue. So in this case, we don't want to mutate. We just want to complete the side chain. So I'll just type F. That will complete that side chain. And then I can use Shift R in order to cycle through the different rotamers and see which one I'm happy with. In this case, this looks pretty good. And I might want to do a little real space refinement around that. I quite like using sphere refine, which I don't have in this version of Coot right now because my computer had an unfortunate accident with a glass of water. So I'm just going to re-add that in right now. So if we right click on the toolbar and do manage buttons, we can add in sphere refine plus. And I'll add that in so that I have it. And if you don't have it, I would suggest doing that. It's useful. And then when we do sphere refine, what you'll notice is that sphere refinement doesn't just refine a single linear sequence. It also refines everything in a sphere around it. So that can be really useful for optimizing non-bonded contacts, particularly in a region where you might have some clashes between different chains or between different linear regions of the sequence. Okay, so I mean, if we were doing this for real, and if you want to do this, I would suggest it. I would go through and fit all these guys separately. I'm not going to do that now for reasons of time, but I would go through each of these truncated residues, mutate them, you know, check the different rotamers, decide which one we think fits best, sphere refine, make sure we're happy, etc., etc. And it should be, in this case, fairly straightforward, even at this fairly low resolution of, you know, 3.7 angstroms. There's not actually that many here, so just do that quickly. All right, is this making sense to everybody? Is everybody still on track? Are people getting extremely bored? It's very hard to tell what's going on Zoom because I can't see anybody, but hopefully this is making some degree of sense. Okay, so now what we're going to do. So I mentioned that the sequence for chain B, or actually for two of the different chains, but for the beta chains, is wrong because what we've done is we've replaced one by the other so that it's deliberately wrong. So if we want to rectify that, what we would do in a real scenario, we might be solving something for which there's a model, which there's a structure already solved at, let's say, 30–40% identity. So our best starting model is going to be a model where we've taken that structure and we've made a simple homology model, a simple threaded homology model, and we can use that as a starting point for rebuilding our structure. So we're going to do that right now. So like it says in the tutorial, we're going to go to an atom in chain B, let's say B6, let's say residue 63, so Control G, B63. Okay. And we want to fix up this chain because we can tell that that it's not right. You know, you can see that in terms of the backbone fit and the side chain fit in this model. Like, just look at this helix. Clearly, something is not quite right here. This does not look like a leucine. It's far too big. So we're going to want to make a homology model where the sequence of this model has been changed based on alignment with the sequence of the other protein, in this case, the other isoform of hemoglobin. What we want to do is we want to make just a copy of this chain. So I'm going to go to custom, copy current chain. And we now have a new model here that if we wanted to, we could save this as a new file. I have already made one of these. I've already saved one of these in the extra models directory. So if we go back here, so we've got a chain B alpha.pdb. So looks like we've got time, so I'll go through this. I'm going to make a new terminal and increase the font size a bit so people can see what's going on. And I am going to open up CCB4. I still use the old school CCB4 because I'm old, I guess. But there is also a newer interface to CCP4, CCP4i2, but I still use this one. You can use either, doesn't really matter. But what we're going to want to run is we're going to want to run, we are going to want to run chainsaw. So if you go to program list and go to chainsaw, we are going to want to put in, I'm not actually going to run this because I've already run it and made the appropriate thing, but we can go through the motions. So we're going to just say prune everything to the beta atom. So just truncate everything that doesn't match to alanine, basically. We're going to, we're going to find what we need, which is we want our chain B alpha.pdb, which is going to be our reference model. And we're going to input a sequence alignment in FASTA format. And we have that in our MISC directory, except we need to tell it that the extension is FASTA. We're going to put in sequences aligned FASTA. And then the PDB out, we can call it whatever we want. Anyway, we'll run that. And what we end up with is a, is a PDB in the right place. Okay. So let's just overwrite the same thing, or we can call it beta 2, whatever. Run that. And because my computer is brand new, I don't yet have a project directory set up. And I won't do that right now for purposes of time. But in your case, that should generate you a threaded homology model of that subunit. Okay. That can be a little tricky. So if you have any trouble with that, please let me know. But basically what this is going to do is this will mutate your alpha model to the beta sequence and adjust the sequence numbering and truncate non-conserved residues. It won't change the position of any atoms. It's just a simple threading approach, like you're taking the sequence of one and threading it through the other. And there is a pre-prepared version of this model, this homology model, in the extra models directory called chain B chainsaw beta.pdb. Okay, so now let's get back to Coot, and I'm going to close CCP4. Yes, I do want to exit. I'm going to delete this one because we don't need it. We also don't need that one. Okay, so I'm going to open the threaded model that we just generated, or in this case that we saved earlier. So if we go back here, so open chain B chainsaw beta.pdb. Okay, so we now have this, and what we will hopefully see, if I just flick between these two guys, is you will see that one has side chains and the other has the incorrect side chains removed, and also the other appropriate side chains mutated. And so you can see, for example, that thing that in the original model was a leucine, which I said doesn't look much like a leucine, has now been mutated. And you can see that, oh, so now it's being mutated to a phenylalanine, right? So that makes a lot more sense. So if we were going through and fixing this up, we would mutate that to phenylalanine, you know, adjust the rotamer to whichever one is closest, and then maybe do a sphere refinement to move that in, right? Okay, but for now, first, what we want to do is we want to merge this model into this model. But to do that, first, we want to get rid of the old chain. So we're going to center on this old chain that has the wrong sequence, and we're going to delete it. So I'm going to go to custom, delete active chain. It's gone. And now I'm going to display the other one. And now we're just going to do exactly what we did before. So we're just going to merge this molecule into the other one, into the original one. So if we go custom merge two molecules, we're going to click the original one, click this one, boom, done. Now we have our molecule merged in there, and it's already, it is a different chain, but in this case, it's supposed to be a different chain, so we don't need to merge chains. Okay, so now one of the nice things in the latest version of Coot, in Coot 0.9 and later, is we have a option called chain refine available in the refinement menu. I'm just gonna, I haven't actually added that refinement menu in here, of course. Let me just see. So yes, okay, so I'm gonna need to add that in there and then reload this. Sorry about this, folks. So remind myself what I need to do. Chain refine, indeed. So I'm going to close all this down, and I am going to copy tutorial misc chain refine, and I'm going to copy that to Coot preferences. Good. And now when I reload Coot, you will hopefully see, yes, we have a new refinement menu, and that has a chain refine thing in it. Great. So I'm now going to reload the stuff that I was just working with. So I'm going to load this guy. I'm going to load the initial model moved, and I'm going to load the chain beans, whatever beta. Where are we? Here we are. Okay, so I'm just gonna, apologies for the repetition, but you know, hopefully that will help with learning or something. I'm gonna delete this guy, and I'm gonna redisplay the other guy and just do what we just did. So I'm gonna merge this one. Great. Now this is the one that we want to chain refine. So I'm gonna center on this. Where was I? And we're gonna try flexibly fitting that entire chain because that's the thing that you can do in the latest Coot, which is quite helpful. So if we go refine, chain refine, you will see that this now allows for flexible fitting of this entire chain. You can see things that are moving around, but without hopefully completely falling apart. And if we have a look in the map here, you can see that it's certainly got a little bit better. Some things that were out of the density are now much happier. There are still certainly some issues here that will need fixing up, but I would say we're probably in a better place overall. Okay, let's accept that and go.
Actually, Ali, I'm gonna chime in because there was just a question in the chat.
Oh yeah,
from Greg. Greg, if you want to unmute.
Yeah,
and
sorry, I
pop in,
can't see
or-
the chat. I don't have any notifications popping up for me of the chat.
Yeah, that's all right. I'm keeping an eye on it for you.
Thanks,
Yeah,
appreciate it.
Maybe it's a little bit off topic, so I could wait till.
I can't hear anything. Sounds like you're talking, but there's not much volume.
Is it better?
Nope, still not better. Let me see if I can find your question in the chat. Okay, for your initial first look maps, what do you prefer for viewing? Coot, Chimera with Coot look, or both? So for an initial first look, I'll usually use Chimera because I find it's better to get a global view of the map in Chimera. but I use both, honestly. But for an initial first look at the map, I'll load it up in Chimera. And then once I have a model that I want to manipulate in any way at all, apart from just rigid body fitting, I'll generally go into Coot at that point. What criteria do you look for before deciding to build secondary structural elements or place a homology model, helices, sheets, etc.? So helices and sheets primarily. You should see, like, it's going to vary a lot depending on the resolution range that you are working at. But you know, if you have helices in particular, should be very obvious sausages, like, you know, isotropic cylindrical sausages at any resolution above about 7 angstroms, really above about 9 angstroms if you have good data. And then at about 4.5, you should start seeing 4.5 to 5, you should start seeing the pitch of the helix. So it should start looking more like a corkscrew. And then closer to 4 to 4.5, you should start seeing well-defined density for bulky side chains. For sheets, at about 5 angstroms, you will see sort of a concave, like density, kind of like concave flat density, kind of like the surface of your hand, which will be the sheet. Once you get to around 4 to 4.5 angstroms, the strands should separate out and you should be able to distinctly see individual strands. Do you ever use Rosetta in your building, rebuilding, outbuilding process? The answer is not as much as I should probably, but I do think it's a very useful tool. There's just a bit of a learning curve to getting it up and running, and the computation is quite intense. Having said that, another option for trying to generate an initial model would be a homology modeling approach that incorporates Rosetta as well as other restraints. So there's a convenient server for that now, which I think was just in the last year or two, called TR Rosetta, and that can be quite useful for generating an initial model. But yes, Rosetta can be useful for refinement. I just don't have the experience with Rosetta to really comment on that at a detailed level. There are better people to consult on that, whom I can certainly, you know, direct people towards. Okay, I hope that answered the question. I'm not quite sure. At what resolution would you decide not to build and go back to getting a better map? So it really depends on what kind of question you're asking, right? And what you need to know. Because it depends at the, you know, what level can you answer your biological question. If you have crystal structures of 2 components and you want to see how they interact, that is, you want to see the overall architecture of a complex, then, you know, 6 angstroms might be adequate, right? Because you can place them in at that resolution. If, on the other hand, you're trying to get detailed insights into the mechanism of an enzyme, then 3 angstroms might not be adequate, and you might want to collect more data until you get to 2.5. So it's really going to depend on the nature of the question you're trying to answer. If you are trying to build a model de novo with minimal assistance from any pre-existing models, then I would say that is going to be challenging at any resolution below about 4 angstroms. It's going to get increasingly easier beyond about 4, and even dramatically easier beyond about 3.5. So if I was getting a map that is 4 angstroms-ish, I might well decide that it'll be a quicker route to a model to collect more data or data on a slightly optimized sample to hopefully get better resolution than it would be just to try to build in. That would be my take on it. Does that answer the question? Okay. Okay. Right. So after you've globally fit this chain, I would go residue by residue, like we did before with that individual helix, and inspect the fit to the map. Going through and filling partial residues using Shift M or K, adjusting rotamers, and locally refining regions, like I already showed you. And you know, we've done a bit of that at this point, so I won't go through that right now. But what I would say is, you know, you'll want to go through the outliers in both the rotamer analysis section. So you can see here the one chain that's missing all the things. That's the one you're going to want to go through all the purple and the red bars and fix everything up. And also have a look at the Ramachandran plot and see if there are any outliers. Actually, in this case, there aren't, both because the Ramachandran plot of the initial reference model we used was pretty good, but also because, like I told you that you shouldn't do, but I did, we had Ramachandran restraints on in that initial refinement. So it's basically pushed everything to be good in the Ramachandran, which may not be the best idea in a lot of ways for an initial build. Okay, let me see. Okay, so there's a missing loop here. So let's have a look at that. So where are we? We want to go to 46B. So what you can see is that we have a loop that should span from 46 to 58. If I take the threshold down a bit, you'll see the density is actually reasonably well defined, except for, you know, maybe one residue over here. It's reasonably well defined, but the model doesn't fit it very well at all. So we're going to fix that up. So let's first of all just remove this little disconnected peptide that's hanging out in the wilderness here. So I'm going to delete zone and remove that guy. And I'm also going to trim the, whoops, I clicked on the wrong thing there. Let me just undo that. So let's delete that zone. That's better. Something that's pretty good. Okay, so now we have something where we have two nice termini. We are presumably happy with our termini. So you can see this, you know, both of these phenylalanines look reasonable. This over here is an arginine, and that seems like it could be reasonable stacking with that tyrosine. So we're okay to build. And now what we're going to do is we're going to fill this loop with, well, actually, let me first real space refine just the termini first, although we've more or less already done that in the global fit, but whatever. And now we're going to want to add polyalanine in here, and I'm going to use the Y shortcut to do that, which was just a shortcut for simply adding a terminal residue. So I'm going to keep going through, just rotating around and monitoring it as we go. And you can see that here it's gone the wrong direction. This one should be heading over there. It's put the C beta where the continuation of the chain should go. So let's just fix that up real quick. I'm going to drag that around. Whoops, daisy. Something like that. Not quite. Come on, buddy. Okay, there we go. Better. And now let's keep going. Keep going. All right, we're doing okay here. And I'll usually real space refine at every few residues just because it sort of accumulates errors as you go. Oops. And that one's gone off a little bit where we don't want it to be. So I'm just going to drag that back because it clearly should be over here somewhere and it's not going the right place. So let's say something like that. And let's check where we are. So we're at 53, this is 58. So we're going to need to fill a few residues in here. So this is actually forming basically like a turn of helix, more or less. 56, and now we're getting there. We only have one residue to fill, and you can see we're nearly at the boundary. Okay, great. So now we have our whole loop more or less in there. I would just refine this into place. So let's refine that and see how we do. It's going to grumble a little bit because all the geometry isn't going to be perfect to begin with, but it should be a reasonable starting point. You can see that a lot of the little balls here are, yeah, so now we fix that up a bit. Everything's a bit happier. Getting there. Maybe this guy should be around like that. Not sure. There. And so on. Okay, so that's building a loop. Hopefully that made sense. So like I just showed you there, so at the point where you're nearly completing a loop, you might find that it becomes difficult to add residues in sensible places. Don't get too hung up on that. Add them anyway until you complete the loop, and then run a real space refine zone to drag the loop into the density. The constraint of loop connectivity will really help in fixing up any misbehaving residues near the join point of the loop. Right, and so these are all polyalanines, so we can do just like we did before. We can go to custom, mutate active chain to template sequence, and now we're going to want to get the sequence for the beta chain. So let's go into MISC, sequences.faster. I'm going to open that with text edit again. And let's get HBB this time. Let's go back over here. Oops. And paste that in and mutate change template sequence. Okay. So now we are done. And now if we wanted, we could go through and fix everything up, but we don't really need to do that right now. Okay, so last bit here, let's go and place the missing heme. So we're going to navigate to a residue that we know is near the heme. So let's go to chain. Whoops, no, I do not. I never do. We want to go to B104. Phenylalanine. And we can see this is near the heme. So let's go to the middle of what ought to be the heme density. And we are going to get a monomer. So go to File, Get Monomer. And in this case, we know the 3-letter code. But if we didn't, we could do Search Monomer Library and search for heme. And it will come up here. It should come up here, I should say. Heme is a little complicated, and a lot of the monomers in the library are kind of lousy and have some geometry errors. But in any case, you've got a bunch of hemes here to choose from. But we are just going to load in regular bog standard heme using get monomer. We're going to type in HEM. We're going to grab it, and here we are. For now, I'm going to remove the hydrogens. So I'm going to go to custom, delete hydrogens. We're going to try to jiggle fit this molecule to the density using the shortcut J. You can see that kind of worked actually in this case, which is good. It may not be perfect though. We might want to have a play with this, but it looks pretty good in that the two carboxylate groups are oriented out of the molecule, out towards the solvent where they ought to be. And the two hydrophobic substituents are located in their appropriate locations. To me, this fit looks right. In a normal circumstance, you would probably want to go around and at least check that this is not flipped and that the two hydrophobic substituents are in their correct places. But I think in this instance, it's actually right because you can see this two carbon atom group is projecting down into that density. Okay. And now we can merge that into the molecule. So again, custom merge molecule, we'll do that. And now we can spherify that into the density. And that's looking pretty good, I would say. So we're pretty happy with that. So this has been a fairly quick overview of everything, but I would recommend going through the complete the tutorial on your own and trying to make the best model you can, starting from that initial model. And that gives you a good entree into validation, because then you can load the reference model and compare your model that you did not looking at that and see how you did, whether you can find errors, how you would find those errors in a realistic circumstance, and so on. Okay, one last thing. Let's jump back to Chimera and compare some of the different maps we made. Because like I mentioned, we tried a number of different approaches to map post-processing. So if you go to the extra maps directory, we have our original unsharpened map. We have our initial map that was auto sharpened by CryoSpark. Then we have the manual one. And we also have a couple of other approaches, one using Phoenix AutoSharp and the other using Phoenix Resolve. We can look at those two in Coot, but I'll just compare these for now. Okay, so let's just set these to an appropriate threshold. So this is a useful command that I'm doing right now, by the way, so you might want to pay attention. So this will set all the maps to enclose the same volume. And that can be useful for maps like these where they are scaled in very different ways. So setting the same threshold would not give us an equivalent view. So let's try like 40,000 or something. That's not quite right. Let's try like 20,000. That's okay. Maybe like 15,000 or something like that. And actually, I don't want the Z-flipped one. I want the original map. And I'm going to close this guy. Okay, so let me open up the volume viewer. So this was the original unsharpened map. And as you would expect from an unsharpened map, you know, the features are not very evident. The lower spatial frequencies dominate. And so we can't see much sidechain density. It's a pretty clean map, but there's not much evidence of sidechain density here, and nor would we expect there to be. However, let's have a look at the automatically sharpened map from CryoSpark. And what you'll see it is, in this case, it isn't a whole lot better, right? It's maybe slightly sharpened, but not very much. And certainly it does not have the features that we would expect from a 3.7 angstrom map. So something has failed in the automatic beat factor estimation process. And that can happen, and that's something to be aware of, particularly at lower resolution. When we manually sharpened it, it got dramatically better. And that's been the map that we've been working with in this tutorial. So that's just, I guess, a little bit of a lesson in don't take anything at face value and really trust your eyes. Like if you see a map that's nominally 3.7 or whatever, seems like the orientation distribution is isotropic, but the automatic map that you download that's supposed to be sharpened isn't looking too hot, I would always suggest trying a few different approaches to map post-processing. Okay. Just looking at a couple of those other ones, we can try opening up one of those now. So I really like Phoenix Resolve. And we can compare between these maps here. So to my eye, in some locations, the Phoenix Resolve map in purple has cleaner, better features than the manually sharpened ones. In other areas, not so much. But it's always a good idea just to try a few different approaches. So you can see certainly in this helix, right, this is a lot better defined using the Phoenix Resolve map. You can see that the corkscrew of the helix backbone is a lot better defined, and the side chains here have a lot better definition. So it's definitely worth trying some different approaches to map post-processing. Okay. Oh, okay, yeah, that's another good thing to try. So I'll just delete that guy. There are some extra cryoEM tools in Coot for dealing with maps. So if you go to Calculate Modules cryoEM, it'll give you a new cryoEM menu. And you can use these for on-the-fly sharpening, blurring, and also resampling. Okay, so let's load that up. So sharpen and blur should be fairly self-explanatory. This is just a B factor, which can be either negative or positive. If it's positive, it's going to blur. If it's negative, it's going to sharpen on top of what you've already applied in the map. But you also have an option of resampling by a certain factor. So this just means resampling the map on a finer grid. That can be worthwhile in cases where your nominal resolution is close to the Nyquist resolution of the data. So close to the resolution where you are sampling limited, right? So let's say your nominal resolution is 2 angstroms and your Nyquist resolution is 2.5. I would then suggest resampling on a finer grid because your data is going to look a little crunchy. Your waters are going to look a little diamond shaped and not very spherical. And resampling on a finer grid by a factor of, let's say, 1.5 or 2 will give you a much more interpretable, nicer map. So that's something to keep in mind. And to show you that, let's say we want to sharpen this, let's say by like -40 or something, -20. Let's resample by 1.5 and make the new map the refinement map. Okay, so now you can see we have a, oops, what have I done? All right, okay. So now you can see we have a finer grid. And one of my shortcuts is just not working. A finer grid, and because I've applied an additional sharpening factor, you can see a little more definition in some of the side chains. So I would use this to create multiple maps to guide building, because with more blurring or low pass filtering, the connectivity is going to be better, but the DL is going to be worse and vice versa. So it's useful having multiple maps available or creating them on the fly while you're building so that you can extract all of the information that is present in the volume file that you're working with. Okay, So this is just an addendum, but I've included here a brief guide as to how to write like a little script in Coot, which you may want to check out because Coot is very customizable. I've written a bunch of little scripts, so have a bunch of other people, and I would encourage you to take those and modify them so they do what you want them to do in your particular situation, because it may not be exactly the same. And the advantage of the modularity of Coot is that's pretty straightforward. There are a lot of different functions present in the API, so present in the set of functions that are provided by Coot, that you can just plug and play in a Python script and everything will just work. And so you can see an example of that here. So I wanted a way to set the map contour level really quickly by just typing a number corresponding to the threshold, the sigma threshold, and hitting enter. So I wrote this little script. So we define a function. We run a couple of quick checks as to whether we have a map displayed and whether we have a map attached to the scroll wheel, so whether the map is active and whether we can adjust the contour. And then we grab the current map contour level, and we just define a function in order to set it to a particular value. And then we do that, we set it to that value. If somebody types in something that's garbage, we will catch an exception, and that will throw up a little dialogue saying that it's got to be a number, you can't type garbage here. And this little bit just defines a little, defines the initial dialogue where you type in the map level. And if we fail those initial checks here, so if we don't have a map displayed or it's not attached to it's not active, if we can't adjust the contour, we will throw up a little dialogue saying that you need a scrollable displayed map. That's all. And then we can easily bind that to a key using something like this, add key binding, tell it what we want the text to be, tell it what the key we want it to be, and then define a function to run when we hit that key. And all you need to do is put those two things together in a text file, dump them in the Coot preferences directory that you're now aware of, and then whenever you load up Coot, it will read that file and it will generate that new function for you, and it will attach it to that key binding. Easy. And all of the functions used, or most of the functions used here, are directly from the Coot API, and you can see the Coot manual here, and it does have documentation of pretty much all of these different functions here. These are documented in Scheme, a different language, but the conversion to Python is pretty trivial. So the syntax is very easily translatable from Scheme to Python. Okay, so I'm a little bit early, but that's all I have for now in terms of the tutorial. So if anybody has any questions or like particular situations regarding their data or anything else that they want to discuss, now would be a good time to do that. I hope this was in some way useful and made a good deal of sense, and that people are following along to a degree.
So what should be the resolution if we want to model a water molecule or some metal ions?
A water molecule or metal ions?
Yeah.
So it depends on how ordered the water molecule or metal ions are as to whether you're going to be able to see them. In my experience, at about 3 angstroms, you will see some ordered water molecules popping up, assuming that the map is isotropic and of a good quality. I would always suggest trusting your eyes on this. If you see a spherical density that is well defined in hydrogen bonding distance of something that can hydrogen bond to it, then I think it's a reasonable hypothesis that it's a water. But if you're seeing that at 4 angstroms, you might want to recheck your glasses and make sure that you're seeing what you think you're seeing. If you're talking about a heavier metal ion, you can certainly see those at somewhat lower resolution. Like we've we've seen calcium ions at 4.1, 4.2, and confirmed their location by difference maps, and they are indeed there. So that's not unreasonable.
All right, thank you.
I have a question. In Coot, can you coordinate like the metals to the main chain?
Yes, absolutely. Well, so generally, the way I would do that is I would create a metal coordination file in Phoenix, which you can do using phoenix.metal coordination, I think, and run a refinement with that, a real space refinement in Phoenix after placing the metal line. And that will generate links that Coot will then read.
Okay, got it. And my other question is, when you are using the trimmings and you install a new version of Coot or Chimera, do you need to reinstall the trimmings?
No.
No, okay.
They should persist.
Okay.
Some of them might break, and if they do, let me know. But so far, they've been reasonably robust over different versions of Coot and Chimera. I need to go through and see if there's anything that should be updated or removed or whatnot, because Coot's changed a little bit over the years. But I still find them quite handy for building, so hopefully they're useful for you guys too.
And all the shortcuts you show us for the keyboard shortcuts are for the trimmings or for Coot?
So most of those are in the trimmings. There are a couple that are native to Coot, like the Y shortcut, I believe, is native to Coot. Control G is definitely native to Coot, but most of the others are in Coot trimmings.
My last question is, when you're doing the kind of the script, how do you know you're not using a letter that is already taken?
Sorry, how do you know you're not?
You're not using like a letter that is already has a function.
Oh, right. Yeah. You're not binding something to a key that's already in use.
Yes.
Yeah, you can look at all the, so I should have said that. Let me just quickly share my screen. If you go to, where is it? Somewhere in here, there is something that will tell you all your key bindings. If you go to edit settings key bindings, it will tell you all of the key bindings, and it will have the standard key bindings that you cannot overwrite. And then it will have user defined key bindings. Some of these user defined ones are actually defined by Paul Emsley and are native to Coot. And some of these ones that I've defined in my Coot installation. So you can have a look through that and just find something that isn't occupied. Or you can look through that to check, basically. Does that make sense?
Yes, thank you.
So I'll leave in the last moments. Do you have any other tips and tricks when people are, let's say, moving from X-ray maps to cryo-EM maps? Something very specific for working with cryo-EM maps?
I don't know. I mean, I think a lot of the tips and tricks in that regard are regarding how to get the best map to begin with, because that's the thing that's really going to affect, how easy it is to build a model. And usually I'll spend a lot of time on trying to do a lot of like local mask refinements and so on to improve. I guess the thing is not to just focus on the global resolution, but focus on the local map quality in all the important regions of your map, and try to improve that as much as you can before you get started, because that'll make your life infinitely easier when you're building. And that applies both for refinement, but also for post-processing. Yeah. So what is the current status of data collection pipelines from auto-generated maps and building maps while collecting data? I'm assuming this is referring to building models while collecting data. auto building models. So the only one that I'm really familiar with is the Phoenix map to model routine. I think there is an EM focused version of Buccaneer now as well, but I haven't tried it. The last time I tried map to model, I still ended up with a lot of disconnected peptides and so on. I suspect at high resolution, so at 2 point something angstroms, it should do a decent job. At 3.5, I'm still not sure about that, but really you would need, I tend to prefer to build, if it's a de novo project, I tend to prefer to build the first model manually, because I feel like I get a better understanding of my data when I'm doing that. But maybe that's a little old fashioned. I don't know. Okay, so it seems like we've run out of questions. I hope that it was a useful useful exercise. Yeah, and if anybody has any other questions, feel free to reach out to me. You can reach me on email or Twitter or whatever platform you find most useful.
So thank you, Ollie.